Hey there, we're going to look at 6.8 today on natural logarithms. And so our objectives are to be able to evaluate expressions involving the natural base and natural log, and to solve exponential equations and inequalities using natural logs. And so we're still in our two standards that we're going to be working on all week, which is ACE 1 and FLQE 4. And so let's talk about the natural base. So remember, the natural base is the letter E, right? The natural base. And that is 2.712, and so on. It's an irrational number. But the natural base is this exponential value. And so when we just have e to the x, it's an exponential growth function because our exponent is positive. And when the exponent is negative, we have exponential decay. And so we see that represented here in these two equations. The red is our natural log of x, and the blue is our e to the x, and we'll have the same here, e to the negative x, and in the red would be the natural log of negative x. Sorry, not the natural log of negative x, the negative log of x, natural log of x. Okay, so with that being said, let's look at some examples on how to work with logs and exponentials. And so this goes back to the properties we talked about yesterday in section 6 and 7. And so being able to convert from exponentials to logs or logs to exponentials. And so remember what goes where, right? So if I have a to the b is equal to c, right? Or, you know, we could use whatever is letters here, but b to the x is equal to y, right? Remember, that's going to go into the natural log of, not the natural log, but the log, right? Base a of c is equal to b. But here's the thing, is this e is our base, right? And so that's going to go here. But I want you to come back up to the note here. The inverse of the natural base, e to the x, the exponential function, is called the natural log. This logarithm can be written as log base e of x, but we usually will write it as the natural log ln of x. Obviously, we say natural log, but the abbreviation is ln, logarithm naturel. It actually comes from the French, with the order of the letters there. All right, so how do we convert this over to a log? So this would be log base e of 20 is equal to x. But remember that this log base e we can rewrite as the natural log of 20 is equal to x. Okay, so again, when we see that log base e, we'll rewrite that as ln. Okay, so the natural log of x is equal to 32. So we're going to convert this over. And so remember that this is log base e of x is equal to 32. And remember what goes where. So the e to the 32nd power is equal to our x. Because remember, what goes where? This is the base of the exponential. This is our power. This is what the exponential is equal to, right? All right. So in example 2, we're going to be looking at how to simplify expressions using e and natural log. And our properties are the same as what we looked at in section 6 and 7. So again, if it's a property for a log, it's a property for a natural log. And so when we look at this, simplifying this completely, we got two rules going on. In this first one, 5 times the natural log of 2, we have power property, right? And so this 5 will be able to come up here. And so we're going to get the natural log of 2 to the 5th plus the natural log of 7. 2 to the 5th is 32. So I get the natural log of 32 plus the natural log of 7. And so now this is product property, and so we'll take the 32 and the 7 and multiply them together, and so the natural log of 224. And so again, when we're trying to, this is also called, you'll see this in some places, condensing logarithms. So we're going from having multiple logs added or subtracted together to one singular log. And so let's look at example B. again, same idea here, right? Now, we could have a minus sign in here and dealt with quotient rule, but everything is addition, so we're dealing with product rule, and we do have a multiplier out front, which means we have a power that's going to end up here. And so we have the natural log of 4 to the third plus the natural log of 9 plus the natural log of t. The parentheses aren't technically needed here in a lot of these steps, but this is just a personal preference. I like to keep the parentheses around what the log is being done of. 4 cubed is 64 plus the natural log of 9 plus the natural log of t. And so this is product rule twice, right? Because, plus and plus. And so remember, product rule says that these are going to multiply together in the end. And so we're going to get 64 times 9. 64 times 9, that's going to give us 36, carry the 3, 57. So we get the natural log of 576 plus the natural log of t. And then again, product rule again, so we're going to get the natural log of 576t. And that's our final answer that we get there. Again, we're just trying to condense this into one singular log when you see the direction of simplify the logs. Okay. The next is a property that we didn't talk a lot about yesterday, but I do want to bring this up. If I have log base 2 of 2, right, that's going to be equal to 1 because 2 to what power gives you 2? 2 to the first gives you 2. Or I could have log base 5 of 5. That would still, again, be equal to 1. And so when we look at the natural log and the natural base, we see the same thing happen. We have an exponential and a log involved with each other. And the exponential and the log will cancel each other out because remember, they're inverse operations. And so we're left with x is equal to x. Same thing over here. The natural log and the exponential would cancel, leaving us just with x equals to x. And so if we know that property, we can use that to solve exponentials. And so we've got 3e to the negative 2x power plus 4 is equal to 10. And so we're still going to use PEMDAS. That never goes away, right? Working up to solve. And so I'm first going to subtract 4 from both sides. And so I get 3 times e to the negative 2x is equal to 6. And then I'm going to divide both sides by the 3. And so I get e to the negative 2x is equal to 2. Now this is where we need to get rid of that exponential. And so I can take the natural log of both sides. The natural log will cancel the e, so I get negative 2x is equal to the natural log of 2. I'm going to divide both sides by the negative 2. And I get x is equal to negative natural log of 2 over 2. Again, these 2's won't cancel. Don't try to do that because that's not what that means, right? And so this is the precise solution. We could go into our calculator and find what the natural log of 2 is. And so we'll do that real quick. And so we'll get the negative natural log of 2, close parenthesis, divided by 2, and we'll see that our answer is negative 0.347. Going to 3 decimal places here. So x is approximately negative 0.347. And that gives us an approximated answer. And this makes sense because e is 2.7-ish. Again, the rounding involved. And so the natural log of 2 would make it smaller than 1. The negative, of course, is going to make it negative, and then dividing it by 2 makes it smaller than what it is. Okay. When we look at example 4, solving natural logs, we're going to use the same properties that we've used before to solve this down to one answer. And again, we're solving an equation, so PEMDAS, again, is our friend, and we're working up to solve this. And so I'm going to first divide both sides by the 3. Now, I know what some of your temptations are going to be. You want to divide that 6x by 3. That's not what happens. This is like being inside a radical. We can't touch the things inside a radical. Same thing. We can't touch the things inside a log. And so we're going to get the natural log of 6x is equal to 5. Now, how do I get rid of the natural log to get the x by itself? I'm going to raise both sides to the base of e. And so I'm going to get e to the natural log of 6x is equal to e to the 5th. E to the 5th is easy to calculate on our calculators. This cancels. We get 6x is equal to e to the 5th. We'll divide both sides by the 6. And so we get that x is equal to e to the 5th divided by 6. And again, if we need the precise solution, we can go to our calculator. And so clearing the previous line, we've got e to the 5th. And we're going to take that and divide it by 6. And we get 24.736. Again, 24.736. 24.736. Okay. For most of these problems, 3 decimal places is the way to go, unless the direction specifies otherwise. Okay. We're going to look at a second example here with an inequality, but it's still the same steps as solving with an equation. We've got to do what we've got to do to get the variable by itself. Now, we got a couple things that we could do. We see this 2 up here. This can come out front first. So 2 natural log of 4x minus 3 is greater than 10, not equal to in this case. Now I can divide both sides by the 2. And so I get the natural log of 4x minus 3 is greater than, not equal to, the 5. Now I can raise both sides to a base of e. In doing that, we're going to get this to cancel. And so I've got the 4x minus 3 is greater than e to the 5th. And from here, we're just solving a normal equation for the x. And so I get that 4x is greater than e to the 5th plus 3. And I'm going to divide both sides by 4. And so I get x is greater than e to the 5th plus 3, all divided by 4. Now, you could get the decimal here, and again, we could go over to our Desmos app and get that decimal answer. And so I'm going to get e to the 5th minus, come back out to our solution, it's plus 3 and then divide by 4. So I'm going to delete plus 3, and I want to take the answer, oops, back it up, enter, and then I'm going to take the answer and divide it by 4. And we'll see that the answer is 37.853. 37.853. So x is greater than 37.853. That's our solution. All right, last thing we're going to look at is compounded interest. We talked about this the other day, the previous wave week, about just doing a regular like quarterly compounding or monthly compounding. Now we're going to look at continuously compounding, meaning every time you earn, that's going to compound back into the interest that you've earned and the principal that is gaining said interest. And so the formula that we have is A is equal to P times E to the RT power. And I like to just call it the PERT formula. And we see here that A is the amount in the account after so many years. P is the principal, which is our initial amount. R is the annual rate. And of course, our rate will be changed to a decimal. And so let's look at example 5. If you were to deposit $1,200 into a banking account, paying 2.5% interest, compounded continuously, what is the balance after 5 years? Well, that's just plugging into our PERT formula, right? So A is equal to the 1,200 times E, and you don't need the parentheses there, E, but you will need the parentheses in the exponent. We're timesing by 5 years, so we'll have 5 times, remember, convert this to a decimal, so 0.025, and so A is equal to 1,200, E to the 0.125 power, and then we would go to our calculator. Let's clear that line. 1200 e to the fifth. Sorry, e to the 0.125. Let's get back to the right screen. 1200 times e to the 0. Gotta love technology. Let's get this right. 1200 times e to the 0.125. And so we see that's 1359.78 cents. That answer makes a lot more sense. Again, 13.89 and 70. 13.59 and 78 cents. So A is approximately 13.59 and 78 cents. Part B, how long will it take for an account, your account balance to reach $4,000? So we're going to get 4,000 is equal to the 1,200 e to the 0.2025. Make sure we get that decimal right. 0.25. But then we're going to keep the TT in this case because we want to know how long is this going to take. So again, we're going to solve this equation. So we're going to divide by the 1,200 first. And so 4,000 divided by 1,200, that's going to be 20 over 6, which is 10 over 3. So this is 10 thirds is equal to e to the 0.025 t. We'll take the natural log of both sides. And so we're going to get the natural log of 10 thirds is equal, and of course the natural log over here will cancel the c, 0.025 t. We'll divide both sides by the 0.025. And again, your calculator is your friend here. And so we've got the natural log of 10 thirds, close our parentheses, times, and if we come back, we're going to divide by 0.025. Divided by 0.025. Get rid of this bottom part. There we go. Oops, that did not change that sign. Delete that sign and put division. And so that gives us 48.158. 48.158. And so what that means is in this problem, T is approximately 48.158. It would take him 48 years to have a $4,000 account balance based on this scenario. All right, so let's look at example C here. How much would have to be deposited in order to reach a balance of $2,000 after 10 years? So we have the final amount, but what we're looking for is the initial amount. So in our PERT formula, right, we've got the 2,000. We're asking what is the P going to be based on our rate of 2.5% and at 10 years. And so we get our 2,000 is equal to P times E. So this will be 0.25 here. Now, we could do a lot of crazy things here, but the easiest thing to do is just divide both sides by this E. Why be crazy here? Use your calculator as a tool. And so we're going to get our 2,000. And we're going to divide it by E to the... E was to the 0.25 power. And we see that is $1,557.60. So coming back, our P is approximately $1,557.60. This is how much he would have needed to initially start with, about a 2.5% interest rate to get $2,000 total after 10 years. Okay, and so that is our final answer there. So with that, I hope you all have a great day. If you have any questions, make sure you hit up the Google Meet, and we will talk about it later. Again, my office hours are 3 to 6 today because of being in my room to pack up all of my stuff. So again, y'all have a great day, and I'll catch y'all next time.